Hello everyone, hope you guys are doing really good. So today we're going to get into the third phase of system representations, and in that we will focus on graphical paradigm. So let's start the discussion. So in previous lectures we introduced all these different representation schemes in the mathematical paradigm as well as in the graphical paradigm. And in the last lecture, we observed how these differential equations are converted into state space representations and how these into transfer functions and all the different possibilities that might be there in terms of their conversions. Now, the next logical question can be how to convert these mathematical expressions into graphical representations. So this question mark is needed to be resolved. So let's quickly do that. So in this pursuit, initially we're going to convert a differential equation into a block diagram. The procedure is quite simple. You're going to start from the nth order differential equation. You'll use that in step number 1 to solve for the highest order derivative in that. In step number 2, you're going to work backwards. And in that, you're going to use the concepts of block diagrams. And remember, we have introduced the block diagrams already. So in that, the summing junction and the takeaway point and the process block and all that we have already discussed. So you can refer to the previous part of this lecture for that. So use the concepts of block diagrams in order to work backwards. And in that, once you're done with a few basic building blocks, in step number 3 you are going to add the input or inputs to the system. So once done, you're going to check whether all the things are well accounted for. So this is going to be the final check that all has been accounted for. So once done, this is going to give you the block diagram. So let's quickly do one example to go through that procedure. It is very simple, straightforward procedure. Let me recall, we have done one very simple uh, spring mass damper system. So let's do that for in order to make it much more simpler. So that was something like in the nth order differential form, it was like mx double dot was equal, rather it was added with bx dot plus kx to be equal to f. So that was your differential equation. So in step number 1, what you need to do is to convert this into a slightly modified form, which is going to be x double dot to be equal to 1 over m minus bx dot would be the first term, then you have minus kx, and then you have the input force in that. So that is going to be used to construct the block diagram. So what I'm going to do now in that particular scenario is that I'll assume that somewhere in the middle of this block diagram I'll have this x double dot available with me. So this thing which is on the left hand side of this equation is going to be available somewhere in the block diagram. So I'll start from there and work backwards. So in order to move forward, what I need, and I can assume that because I will use x dot and x for in order to convert this into a block diagram, so I need to have an integrator block for that. So that was defined to be taking this shape because it is in the time domain. We're going to use this notation for that. And once this has integrated, you are going to have x dot available. Now, furthermore, you can have another integrator added in it, and that is going to give you x. Now, you can now obviously see that you have x double dot available. you have x dot as well, you have x available as well. So I'm going to now observe what is happening in the block in the differential equation, in the modified differential equation, and I can make connections with the block diagram now. So the very first thing that I can observe is that I need x dot to be multiplied with b and then have a negative sign associated with that in order to come up like one of the elements in the x double dot term. So that would be something like done very simply. Take the x dot from here, have a takeaway point for that, and have it multiplied with b, and that is going to be like a signal bx dot available with you. So if you have this summing junction available somewhere, let it be drawn at a kind of displaced manner. Let it be like over here. So I can go all the way to that summing junction and provide this bx dot signal over there, but with a negative sign. Now moving on, I can readily observe that you have kx is also needed in this expression. So I'm going to take away x from here, sorry, and multiply that with the spring stiffness K, and that is going to give me Kx. And that is once again needed in this summing junction right over there. And since you can also see that this is going to require a negative sign with that, so I'm going to place that negative sign as well. So on the summing junction, you have the two signals available, minus bx dot and minus kx. The other thing that is needed is the input f over there. So that can be added from this side, but with a positive sign. So now you can see that minus bx dot minus kx plus f is available. Now that is going to be provided as a signal to another simple block, which is going to have a gain of 1 over m with that. And that obviously is going to give me and you can see on the expression as well, that is going to provide me equal to the x double dot. So that is going to be accomplished over here. So now you can see that everything is well connected over there, and that is your block diagram. The conversion from state space model to a block diagram is even simpler, and we can do one very quick example, and that is going to further illustrate how it can be done. Actually, we have done it in the previous example as well. Just to illustrate a couple of additional points, we are going to do another example. Let it be like you have the same system structured in a state space model, but now you are going to use in a state variable vector. Let it be like you have momentum term added in it as a state, and then you have the displacement as the state as well. But if you construct it in this fashion, you are going to have your A matrix to be minus B over M, and this is minus K, and then you have 1 over M over here, and then you have 0 over here. And that is when added with the input force. So that is going to be like this, which is equal to the state dynamics, which are P dot and X dot. Now you can see that these are already in the same formulation that was needed in step number 1 in the previous example, but now we are going to use a very simple straightforward arrangement to start from, let's say, P dot, and indicate in a signal arrangement that you have this thing available somewhere in your block diagram. And similarly, let me use a different color now. You have the x dot available somewhere as well. So let it be like another signal available in the block diagram, which indicates x dot. Now what I'm going to do, I'm going to have this P dot further explored. So this P dot is, when integrated, this is going to give me the momentum term P, And similarly, when x dot is integrated, this is going to give me the displacement. Now I can see what is happening in the first expression over here, and I can try to cover all the basics. So P dot in that case is minus B over M times P minus K into X plus F. So I'm going to try to account for that in my block diagram. So that would mean that I need P from here. So I can have a takeaway point, multiply with B over M over here, and then I can provide that in a summing junction with a negative sign over here. So this is going to be, in that particular sense, B over M multiplied with P over there. And with the negative sign, it is going to be covering for one of the components, one of the elements in the equation. And then you can see that it needs to have minus K into X added in it as well. So I'm going to assume that there is going to be X available, and that can be multiplied with K to give me, in that sense, with a minus sign, Kx. So that is available as one of the elements. And now I can see that that is needed to be added with the input, which is the force, applied force to the system. So that can be added with a positive sign as well. So this has accounted for the first line or first equation in the state space model. Now I'm going to revert back to the green color and see what is happening with the x dot, and that is x dot is equal to 1 over m times p, so it uses p obviously, and that is it. So let me try to do that as well. So I'm going to take away p from here, have it multiplied with 1 over m, and I'm going to provide that over here because that is actually x dot, and that is it. This is your block diagram that you wanted to have to convert the state space model, which is in the mathematical formulation, into a block diagram. And obviously we can go in reverse direction in order to construct state space models from block diagrams as well. So to start with, we're going to have, in this case, a block diagram, and we can very easily construct a state space model. You can readily identify from the block diagram that states are available after the integrator, x and p. Now, if the output from these integrators are states, the inputs to these integrators are going to be the time derivatives of the states. So I can simply write those down like p dot and x dot as a vector on one side. And I can see the states ordered in the same fashion as well, p and x. Now over here for the p, you can see p dot, you can see that this is going to be equal to whatever is being fed to the summing junction. So you can see that it accounts for quite a few terms in that. But the term corresponding to p is going to be written first, which is over here. So that is going to be minus b over m placed. P is multiplied, but that is already available in the vector p and x. The second term which is available is that coming in from the other state, x multiplied with k, which is equal to kx, and that is also with a negative sign. So you can see minus k indicated over here. So this would mean that p dot is equal to minus b over m times p minus k times x. And then obviously one thing that is still available in this summing junction is this input, like the force acting on the system, because this is the input, and you can see the structure of the state space, which says that x dot should be equal to a times x plus b times the input. So that is for that reason structured with a positive sign in this fashion, that you have got something multiplied with force. And that is, in this particular case, force is directly being fed to the summing junction, so that's why it is going to have a coefficient 1. So let's now see what is happening with the other expression, x dot. And you can see that x dot is coming in from this side, which is shown in green. That accounts for the p in that. So I can simply, for that reason, write down corresponding to this place, which corresponds to the p. So this multiplied with p is going to be written down over here. So that's why it is going to be 1 over m indicated, and that is it. There is nothing corresponding to x, so that is going to remain 0, and there is no input to the input contribution in that, so that's why it is going to be 0. So this is your state space model. And if you in that particular sense require, for example, a specific output equation to be written down, you can obviously write that one down using this simple notation. In this case, d is 0, so that is well understood, but you can obviously select any of these states to be declared as the output. So you can obviously do that as well. And if you need to further convert it into a differential equation, all you need to do is to take this form in and use the Cramer's rule that we have already studied to construct that. In the graphical paradigm, we may require the block diagrams to be converted into signal flow graphs so that subsequent analysis can be performed. So in that particular scenario, we have to introduce ourselves with signal flow graphs as well. But I'll do that indirectly. So I'm going to start from a block diagram, and I'll try to kind of convert it into another graphical format, which is called signal flow graphs. And by that, indirectly, I'll try to explain what is meant by signal flow graphs. So I need to draw a block diagram. And for that, I can start from the basic state space model, like x dot to be equal to ax plus bu. I can start from there. And the output equation, which is in a generic form for linear systems, to be like this. This you have seen so many times. So I'm going to convert it into a block diagram and then into a signal flow graph. So first of all, I need to see that somewhere in my block diagram I should have the dynamics of the state indicated. So that would be x dot. It may be a vector as well, which is then integrated. So in this particular case, I'm going to try to use the S domain. So the integrated in S domain is 1 over S. And that would mean that you have X available. Now, that can be further manipulated in this fashion, that you have taken this X as a takeaway point and multiplied with matrix A, which is the state coefficient matrix, and then you have added it through this summing junction to create one part of the x dot. Now the other part of the x dot, as you can identify readily over here, that it is going to be b multiplied with u. So I need to get that bu from this side, which is going to obviously have a block corresponding to input matrix B, and then you have the u provided as the input to it. Now, with this realization that now I've got this x dot available with me, x dot available available with me, which is going to be equal to ax coming from this side plus bu coming from this side. So then I have to account for the output equation, and for the output equation you can see that output is equal to c multiplied with x. So x is available over here, I can make use of that, and that would be when you multiply with the output matrix C to get Cx, and that is then added with something coming in from somewhere else. Let me try to see that to generate output Y, but that something else is actually D multiplied with U, so I can get that from this side. So let me try to take away from this point, multiply with D from here and drop it over here with a positive sign. Now in this case I'm going to remove this so that there is no ambiguity in this diagram. So now at this particular stage you can see that output has been acquired, which is equal to Cx coming in from this side plus du coming from this side through the feed forward matrix. Now once you have got this block diagram available with you, you need to transform it into a signal flow graph so that I can make use of Mason's loop rule or Mason's gain formula to further analyze what is happening inside the system. We will see that later on, but at this particular stage I need to convert this graphical block diagram into another graphical form of representation called SFG or signal flow graph. So let's try to do that. I'm going to use a different color now. So the very first thing that I'll do, I'll try to kind of indicate the system variables. So the very first system variable can be starting from this side, u, and that is right over there. So I can take u as a node over here. So this terminology is important because we will see that later on. So node is important, and these are going to represent the system variables. Now the other thing that I can see that there is another node somewhere over here which gets something from this side, which is multiplied with matrix A and then this X generated somewhere in the subsequent part of the signal flow graph. So what I'm going to do now, I'm going to connect U with this node, and in between I'm going to think about what is going to be the gain from U all the way to this node. From this node to this node, what is going to be the gain in between? So you can see that from the block diagram, U is available over here and AX is getting in this node. So in between you have a gain of B added to it. So I'm going to add or write B as a gain to this path. So there is a concept called branch, and there is a concept called path in this process. So from this node to this node, there is an in-between gain that is added to the system variable U, and that is going to be available at this node. Now once added with the AX coming in from this side, it is going to generate an output. An output would also be a signal, and I'm using or emphasizing the word signal over here because that's why it is called signal flow graph. So that signal is obviously at this particular stage indicated to be x dot, but once multiplied with 1 over s gain, which is actually the integrator, it gives you x as a node over here. So this node is now x. So from x dot to x, obviously there is going to be an integrator in the middle. So that is given as a gain to this branch. Now you can readily see that this AX was coming in or originated from this X node because of the block diagram over there. So you can readily translate or connect that as well. Now with this realization that you have got now parked somewhere over here, you can see that what is going to be the next step. So from X all the way to Y, you are going to have in the middle this gain C added in it. So that is going to be added like this, that you have generated another branch with a gain of C in it. So that is going to give you another node over here, which is corresponding to the output Y. Now on top of that, you can see that this node generating Y was actually having another branch connected to it using D as a gain over there. So let me add that, and that starts from U all the way to this point with a gain of D. So I need to clean this diagram up, so I'm going to remove these designations. These are not needed anymore. So at this particular stage, you can see that you have converted this block diagram into a signal flow graph. Now, this signal flow graph, I'm going to further emphasize over here that this is going to have nodes U, X dot, X, and Y, which correspond to this location, this location, this, and this over here. Out of these nodes, U is the input node from where all the branches are emanating or getting out of it, and there is an output node at which all the branches are getting into it, and there is no branch coming out of that as well. So in the middle you have a path starting from this U through X dot through X up to Y, and there is another forward path all the way directly connecting input to the output through this matrix T. And then there is something like a closed loop over here. So you can see that from X dot to X and then back to X dot, there is this closed loop over there. So that concept is also added in the mix as well. So loop, indirectly the gains of the branches as well as loops as well as the forward paths and all that. So with this realization that these concepts that we have introduced over here are going to be the terminologies which we will further explore later on, but at this particular stage these terminologies are corresponding to signal flow graphs, which you can readily see that these are relevant with the block diagram representation. So this is how we convert a block diagram to a signal flow graph. It is actually by inspection, but when you have to inspect, you have to be aware of the terminologies of the signal flow graphs, the nodes, the branches, the paths, the forward as well as the loops, as well as the gains associated with all these branches in the middle. So with this realization that you have converted a block diagram to a signal flow graph, this is the procedure, but we have to further explore or explain the signal flow graphs as well, so that we may use them for better analyzing the systems. First of all, let's get the terminologies right. The very first terminology was node, and this represents system variables. Now in this particular case, you can see the system variable is at this particular stage the input U, X dot, X, and Y. The other terminology is branch. So from nodes, you can see that there are branches coming out and getting into the nodes. So actually these are the lines or the signals connecting the nodes. But on top of that, these branches are going to have gains as well. So for example, in this particular case, you can see that this branch from U all the way to X dot is connected over here, but actually it is also associated with a gain B, which acts as a multiplier to U. So in that particular sense, X dot is going to have an influence coming in from U, but after getting multiplied with this gain B. So you are going to have BU added as an influence to this node X dot. Obviously there is another influence coming in from this side that we will add later, but at this particular stage, from this node to this node, you have a branch, but this branch has got an associated gain associated with it, and that is going to be available at the connected node. Moving on, there is this concept of path that we identified. Now, this path can have two different meanings associated with it. One, what we call the forward path. So that path is going to be starting from the input node, from where all the branches are getting out. So starting from the input node, the connected path having all these branches all the way to the output node, that is going to be the forward path. So in that particular sense, you can see this definition that the forward path is going to be associated with the path which connects input node to the output node. But there can be closed paths as well. So that is another associated terminology. In that particular sense, it is going to be a path which starts from the same node and ends at the same node as well, which starts and ends at the same node. We have one available over here. You can see that like a path starting from X dot having a gain of 1 over S and then having a gain of A gets back to X dot. So this is a closed path. Moving on, there was this concept that we introduced corresponding to loop. Obviously this is related with the closed path. So actually I'll write that closed path, but I must be aware that I'm more interested in the gain of this loop, of this closed path. So in this particular case, like the example that we have just mentioned, you are going to have the 1 over S as one part of the gain and then A as the other part of the gain. So you are going to have these two gains added in a loop. Moving on, in the loops you have another associated thing to be consciously aware, and that is that you are going to have the concept of touching and non-touching loops needed, especially for the subsequent analysis. So in this particular scenario, the example would be that this path starting from U all the way to Y using the feed-forward matrix in the middle, this loop is non-touching to it. So there is no node which is being shared by this forward path. So in that particular case, this loop is going to be non-touching for the forward path from this u through d all the way to y. But if you consider the path starting from u through this route all the way to y, having all these intermediate nodes available as well, then for that this loop is a touching loop. So we will use this concept of touching and non-touching loops in constructing the Mason's gain formula. But in that, you must be aware that what is meant by touching. Touching would mean that there is at least one node which is being shared by that particular forward path. Non-touching would mean that there is no node being shared. Now, with this realization that you have got almost all the terminologies indicated, now I think we are at a better place that we can start discussing the Mason's gain formula. Now, Mason's gain formula goes something like this, that you can compute the gain of a system, which is not that complex. It is just like the ratio of output over input. You can compute that if you can add these factors together, p's and deltas. So these can be k, p's and deltas divided by a big delta which is called a determinant of a system. Now let me try to label those terminologies as well. G is gain of a system. Since you can see that this is being indicated like a ratio of output and input, it means that when input is provided to the system, which generates after passing through all these forward paths, which generates an output, how much gain the system has imparted on that input. So that is the overall gain of the system that we are interested in finding out. And that can be computed if you multiply the path gains or to be precise, forward path gains with the cofactors. Now, since we have used this letter K in that, so K is the number of forward paths. I'm using the word forward path, but we have already introduced it already, that you are going to observe the signal flow graphs and see that from the starting node or input node all the way to the output node, how many different or distinct paths are available. So one of those paths, each one of those paths is going to be considered as forward path. So what you have to do is, in that sense, that find out the gains of those forward paths and multiply with deltas or cofactors of that forward path. But what is that cofactor? That is still to be known. We will see that in a moment. But this big delta is what we call determinant of a system. This is very important because eventually when equated to 0, it is going to give you the characteristic equation of a system, which is going to be in classical control paradigm, the basic starting point of analyzing the systems. So we will try to compute that as well. So in this particular case, you can now see that the formula is being given over here, that you can compute the gain of a particular system when you have this numerator and denominator computed. But what are going to be the formulas corresponding to these terminologies? Let's explore that as well. Finding out determinant is the foremost thing. That is equal to 1 minus sum of all the loop gains in a system. So you are going to count in a system that how many loops are there, and all those gains corresponding to those loops are needed to be summed up in this particular part of the formula. And then you have to add with sum of all possible combinations of two non-touching loops, A and B. So this is going to be all the possible combinations of two non-touching loops added in it. And then once again you have to reverse the sign. So if this is minus, this is going to be plus, then minus, and so on and so forth. So then you are going to sum all the possible combinations of three non-touching loops. So that would be LA, LB, and LC in that. And you will keep on doing it until up to the point when you find no further possible combinations of the non-touching loops. So that is going to be the general formula to find out the determinant of a system. For simple signal flow graphs, this would not be that problematic, but once you're going to have more complex systems, then obviously you need to be very cautious and careful to find out that what are the non-touching loops and how different combinations can be constructed. Now moving on, once that determinant is available with you, you can think about what is going to be the delta k's, or which are called cofactors. So this delta was determinant, and delta k's are the cofactors. Now in that particular case, it is going to be the cofactor of kth forward path determinant of the SFG that we have constructed with the loops which are going to touch the kth forward path removed. So that would be in a sense that you are going to find out the cofactor of that kth forward path with the loops which are going to be touching the kth forward path. Although the definition of cofactors seems a bit complex, but actually in terms of its construction it is quite simple. All you have to do is to think about this delta or determinant that you have computed already, and for the selected forward path just remove those touching loops from there and then see what is the remaining cofactor and find out that using the same formula for that. So that would be very easy in terms of constructing the cofactors once you have computed the determinant and identified all the forward paths. Now let's try to apply this Mason's gain formula on the system that we have drawn already. So in that case, I must rewrite that the gain formula is when you take the summation of pk's and their cofactors over the determinant. So that is going to be requiring the forward paths to be computed first. So what are those? So you can readily identify that the very first forward path is starting from this node in this direction all the way to the output node. So that is forward path P1, if I may say that. So P1 is going to have the gain something like this, that you have B, then 1 over S, and then C. But because these are matrix valued, so I will be conscious of the size of these matrices and the order of multiplication. So if I take the liberty for a moment, we can counter check that later on, that I'll write C first and then B divided by S, it is going to be the gain of forward path shown in yellow. So this is one of the forward paths. The other forward path can also be identified. Let me use a different color now. So you can readily see that there is this forward path starting from this node but going in this direction all the way to the output node. So that is going to be the second path. So let it be like P2, and the gain of this is simply D. So these are the two forward paths corresponding to this diagram. So this is going to be step number one. Step one. Step number two would be to find out the loop gains. Loops and loop gains. So in that particular sense, let me try to highlight with a different color now. So there is the definition of loop is quite obvious. You said that you are going to start from one node, but if you, after completing the full route, you get back to the same node, this would be the loop. So this loop is available over here. So this loop can have a gain associated with it. I can write that one down. So that is going to be A over S. So this is the loop gain of loop number one. But we have to be conscious that is there any other loop available in this whole diagram or not. So although this is kind of a simple straightforward signal flow graph, but you must be conscious that whenever you have signal flow graphs, you need to account for all the loops that are possibly there. So there is, I think there is only this loop. There is no other loop which kind of goes back to the same node in this diagram. So I'm confident now that there is no other loop other than that. So this is going to be step number two. Now moving on, having a step number three in that sense, that you have to compute the delta or the determinant. So this determinant was defined to be delta, which was equal to 1 minus sum of all the individual loops. Now, in this particular scenario, since there is only one loop, so the remaining expression, sum of all combinations of two non-touching loops, becomes redundant. So there is no need for that. So I'm going to cross that one out. So I'm going to be only interested in, because of the way the diagram is constructed, so this is going to be 1 minus the loop gain, which is A over S. Now at this particular stage, because we are considering, we have started this signal flow graph from the state space model, so I must be aware that these A's, B's and C's are matrices. So for that reason, rather than having 1 minus something, I'll place identity matrix minus A to be consistent with the matrix manipulation. So with this realization that once manipulated, this is going to be Si minus A over S to be the determinant for this particular system. Moving on, now we have to see for the two forward paths what is going to be delta 1 and delta 2. So this is going to be step number 4 in that sense. So delta 1 is going to be the cofactor when you remove that forward path corresponding to that. So when I'm considering the forward path to be this, obviously I can see that the only loop that is in there is going to be also removed from the system. So there is no other loop in that. So for that sense, the delta 1 turns out to be 1 minus 0. So this is going to be equal to, if I may say that, identity matrix, because this is matrix manipulation. Now for delta 2 on the other side, if I consider what is happening with this forward path, you can readily see that this loop is non-touching with this forward path. So that is going to be included in the mix. So that would remain in a similar fashion, identity matrix minus A over S, which is the loop gain, which is going to give you Si minus A over S as the expression. So once you have got these 4 steps involved now or resolved, then you can have the step number 5, which is the final step in this whole mix, which is going to make use of this formula number 1, equation number 1. So 1 would indicate in that sense that you can have P1 delta 1 plus P2 delta 2 over the determinant to give you the gain of the system. So we can do that now. So this is going to be equal to P1 is CB over S. So in that particular sense, I'll say that CB over S can be written. Then delta 1 is identity matrix. So that's there. And then you have P2, which is D, and then delta 2, which is obviously already written down, Si minus A over S. You can see that delta 2 over there. So that is written and then divided by the determinant, which is also already computed, Si minus A over S over here. Now with this realization that you have got S appearing over here and over here, which can be cancelled with the S over there, so I can now once again rewrite this whole expression. So that would mean from this side upwards, that would mean that this is equal to, gain is equal to CB plus D into Si minus A over Si minus A. Actually, Si minus A in the numerator or denominator can be seen that you have appearing the same matrix appearing over here, so that can be cancelled corresponding to D, but for the CB this is needed to be accounted for. So I'm going to take a liberty now, and I'm going to bring this upwards because this is a matrix in the denominator. So I can have C, then you have Si minus A taken inverse of, added in it, and then multiply that with B, and then you have plus D Si minus A multiplied with Si minus A inverse. That is going to be identity matrix, so this is simply D. Now if you have that, this would mean that gain is equal to C Si minus A inverse times B added with the matrix D. So this is your gain of the system. But at this particular stage, I must make you recall that actually this expression was already computed when we were trying to find the transfer function from the state space model. And this was exactly the same expression. This expression that we have written down over here is the same expression that we have seen in that case that was defined to be equal to y in the S domain over u in the S domain, and that was this expression already. So I'm going to write that one down, same as in previous discussion. So this is a very good observation that from the signal flow graph we can readily identify the same expression that was needed earlier while doing the analytical approach in previous part of this lecture, and that is reappearing once again over here. So that's one strength of the signal flow graph, that it gives you those tools to get back to the analytical paradigm and see how graphical systems can be mapped onto the analytical approach while preserving uh, all the relevant details. So that's the strength of the signal flow graphs. Now I can rewrite this whole expression once again, that this gain is equal to the output over input. But then if I can write down this as C and then further elaborate this inverse, that would be something like you take the adjoint of Si minus A over here and divide it with the determinant of Si minus A over there. So that is going to be then multiplied with B, then you have added with that the D matrix or feed-forward matrix. So this is, in that sense, a ratio between the two expressions, one that you have got in the numerator in the S domain, and the other which is in the denominator also in the S domain. Now this denominator in that sense in the S domain is actually equal to determinant of Si minus A, and when this is equated to 0, this is what we call characteristic equation. And that is needed to be highlighted as well, because this is an important observation. This characteristic equation is going to give us some insight of how the system is going to behave while plotted on the S plane. And what is that? Let's try to explore that. Let's do one little exercise to further strengthen the understanding. So in this particular example, I'm going to make use of spring mass damper system, but I'm going to start from a block diagram so that that process that we have just explained in the graphical paradigm is well understood. So I'm going to have the input provided to it as force, which is then multiplied with this block of 1 over m. Then it is provided to a summing junction, and out of that summing junction comes a variable which is x double dot, which is acceleration in this case, which is then integrated 1 over s, because we are moving in the S domain, to give us the velocity, and then integrated once again over here to give us the displacement. Now with this realization that the velocity is then taken from here, multiplied with b over m, and provided with a negative sign to the summing junction, is going to be one of the contributing factors as the system's differential equation is structured. And then you can take the x as well, like a takeaway point, and you can multiply with the gain of k over m over here to provide with a negative sign over here in this summing junction, and that is going to be the other contributing factor. So in that particular sense, x double dot is going to be equal to the factor coming in from this side, which is f over m, minus this feedback coming in from the position side, and this signal coming in from the velocity side. So now I can try to make a signal flow graph so that this procedure is further strengthened. So in that case, we said that we're going to have the nodes. Let me use a different color now. So we are going to have the nodes. So in this case, the node is the starting node or input node is F. Then you have a branch which goes all the way to the second node, which is x double dot. And the branch has got the gain of 1 over m. And this is what I'm going to observe from this diagram. So from F to x double dot, I have 1 over m in the middle. So from F to x double dot, I have 1 over m as the gain in the middle. So I'm following observing the block diagram and constructing this signal flow graph. So at this summing junction where x double dot is there, I have two signals appearing. So I'm going to indicate those. and then I have this another branch which goes all the way to x dot node, but now you have 1 over s as the gain in the middle. But from x dot, I can now readily see that there is this uh, arrangement available as a feedback with minus b over m as the gain of it. Now, once you have the x dot available, then you can have another branch taken from here all the way to x over here, which is being treated as the output node over here because this displacement is the required output in the system. So you have 1 over s as the gain, and from x you have this signal available to construct x double dot, and this has got minus k over m as the gain of it. So this is k over m, but this is minus sign, so this is for that reason minus k over m. Now this is it. This is your signal flow graph. But then you have to use, in the next step, another conversion is needed to find out the analytical expression or the transfer function of the system or the gain of the system. So for that reason, we are going to make use of Mason's gain formula, and let's try to implement that. And that is going to indicate that you have something like output, which is x, over input, which is f, to be constructed like a gain of the system. So this is going to be equal to, in this particular case, you can readily identify that the path starting from the input node all the way to the output node is only one. So for that reason, you're going to have only one path available, forward path available, and that gain is going to be 1 over m multiplied with 1 over s multiplied with 1 over s. And that is quite obvious, 1 over m, 1 over s, 1 over s. And that is then needed to be multiplied with the cofactor for this forward path. So I'll write that one down later on once I've got the determinant computed. So this delta is the determinant, and that can be computed using the formula that we have already written down. This is 1 minus sum of all the individual loops plus sum of all the loops, two loops which are non-touching with each other, all the possible combinations of those. So it goes on and on, but in this particular case you can readily see that there are only two loops, but these two loops are touching each other. So for that reason, this is going to be taken away, and there is no other further extension of this formula. So for that reason, I can write that one down like this is going to be 1 minus sum of the individual loops. So the loop number 1 is going to have this arrangement. So this is 1 over s multiplied with minus b over m. So I'm going to write that one down. This is going to be minus b over ms. So this is one of the loops, and then you have the other loop, which is a bigger loop, 1 over s squared, and then minus k over m. So that would be minus k over m s squared. So with this realization that you have got these as the two loops, loop number 1 and loop number 2, so I can now further expand it. So this is going to be equal to 1 minus, and then internal minus is going to make it positive, b over ms minus k over ms squared. But now this minus is, because of the minus on the outside, turned into positive. So that would mean that you have got, for that reason, one expression. Let me write that one down over here, which means that this determinant is equal to I can have ms squared indicated. This is going to be ms squared plus bs plus k, and I can use that in equation number 1. This would mean that you have got 1 over ms squared. What I've done in this case, I've multiplied 1 over m with this and that, so there's going to be 1 over ms squared divided by this delta that you have computed already. So this is going to be ms squared plus bs plus k over ms squared. So obviously you can cancel this with that, and that is going to be equal to the output over input, or the gain of the system. So I can further manipulate that. So this is going to be x over f, which is equal to obviously 1 over ms squared plus bs plus k, and this is your transfer function. This is gain of the system, or transfer function. Now you can readily see that in this particular scenario, the denominator, which is in the S domain, when equated to 0, this would mean that you have characteristic equation available, and in this case you have ms squared plus bs plus k to be equal to 0 as the characteristic equation. Now this would mean that you have two roots of this equation, and these two roots, when plotted on the S-plane, are going to be the poles, which are going to indicate whether your system is stable, unstable, or what kind of response you're going to expect. So generally what is needed is that the characteristic equation is, when solved, the roots or poles are plotted on S-plane or complex plane. And this S-plane in a simplistic arrangement is going to have a two-dimensional arrangement. This horizontal axis is going to be the real part of the roots, and the vertical axis is going to be the imaginary part. Now, in terms of system's stability, it is quite obvious that whenever you're going to have the real part of the roots to be positive, you are going to have your system to be unstable. Why so? Because in that particular scenario, you have, once solved, you're going to have your system response having terms like e raised to power positive alpha t. So that positive sign is going to indicate that you have the exponential rise expected in your system. So in that particular sense, you are going to expect that your systems will behave somewhat in this fashion, that they start from somewhere, but then you have the exponential rise in the response of the system. So for that reason, these are going to be in the time domain, when plotted using the inverse Laplace transformation, are going to have unstable response. But if you have your poles, let's say on the left hand side over here, then you are going to have the stable systems. So in order to have your system to be labeled as a stable system, all of these roots or poles are needed to be placed on the left-hand side of the S-plane. So in that case, you are going to have e raised to power minus something as part of the response, and that would mean that you have uh, a decay in the response in the time domain. So you are going to start from somewhere, but then you have the exponential decay in the system. So that would mean that eventually the system will settle down or get stabilized. So in that particular scenario, you can make a comparison that any of the poles when plotted on the right hand side are going to make the system unstable, and any pole which is going to be plotted, all the poles when plotted on the left hand side, then the system is going to be termed as a stable system. Then this is the story when you have the poles on exactly on the axis, on the horizontal axis, but whenever you have poles on the imaginary or some part of the pole, like a complex conjugate on the imaginary side, then obviously you're going to have something like this arrangement, and that would mean that you have some sort of oscillations in the system. So in that particular scenario, the system's response would look something like this, that it is going to have a decay, obviously, because of the negative side, and that decay is going to be somewhat delayed, or a slow decay, if I may say that, as compared to the one already drawn over here. So as compared to this decay is going to be much slower delay, because it is closer to the origin, or closer to the axis. So in that particular sense, the decay is indicated, but then obviously because it is having an imaginary part, you are going to expect that there is going to be oscillations in that, something like this. Although these are decaying oscillations, but oscillations are going to be there. So in that particular sense, you can see that the characteristic equation, when plotted in terms of its roots and poles on the S-plane, is going to define whether the system is stable or unstable or marginally stable. And if it is stable, what kind of decay, or how quickly it is going to stabilize, or what kind of oscillations you're going to expect in that. And if it is unstable, what kind of oscillations in that, and what kind of instability is there. That is going to be an important observation. So for that reason, this S-plane is an important tool to have in order to understand or comment on the stability of the system. And that is what we have reached to this particular stage after we have got the characteristic equations, after we have understood or found out the transfer function. And that is why the Mason's gain formula is going to help us out to transform the graphical representation of a system into an analytical expression, which we can further manipulate and observe to comment on different aspects of the system. So that's why this is important. So guys, this is all we wanted to cover in this discussion. I hope that you've learned something, but you must do some problems on your own, some exercises on your own, so that you can further strengthen the understanding. So with this thought, bye bye.